We've never directly witnessed their presence, yet their existence is known to us, hiding within densely packed star clusters, or meandering through the galaxy's dusty pathways. There, they hunt stars or devour entire planets. Our Milky Way might host millions of these mysterious voids, the ultra-dense remnants of deceased stars. However, in the far-off corners of the universe, there's evidence of something far more ominous. A breed of black holes that has grown to unfathomable sizes and possesses devastating powers. Just how immense, violent, and peculiar can they become? Just how colossal, turbulent, and uncanny can they grow? A new era in astronomy has brought to light a universe long shrouded from our view. Cutting-edge instruments sent into space have been finely tuned to detect high-energy forms of light, X-rays, and gamma rays, unseen by our eyes and impeded by our atmosphere. Meanwhile, on solid ground, advanced telescopes equipped with cutting-edge technologies counteract atmospheric distortion. They peer into the farthest reaches of the cosmos and into distant sources of light and energy. In some remote galaxies, astronomers are now discovering evidence that space and time are being torn apart by eruptions of unimaginable scale. We are only beginning to grasp the profound impact these outbursts have had on the cosmos, on the structures of galaxies, the distribution of stellar and planetary materials, and ultimately, the very fabric of existence on Earth. Understanding the causes of these eruptions has led to a new perspective on cosmic history. In 1995, the Hubble Space Telescope embarked on a mission to fill in the gaps of that history. Astronomers meticulously selected tiny patches of sky between stars. 4 days on end, they focused Hubble's gaze on remote regions of the universe. These Hubble Deep Field images offered remarkably clear insights into the universe in its infancy. What intrigued astronomers were the smallest galaxies, dotting the vast expanse of the cosmos. Only a few pixels on Hubble's detector. Most of them lack the majestic spiral or elliptical forms of the large galaxies we observe nearby today. Instead, they appear irregular, resembling haphazard assortments of stars. The Hubble Deep Field affirmed a long-standing notion that the universe likely developed through a series of building blocks, with small galaxies gradually merging and coalescing into larger ones. This pattern is evident when observing the universe. Numerous galaxies orbit each other, some reliant on the gravitational dance of neighboring galaxies. While some collide, others tear each other apart. Gravity orchestrates these movements as galaxies converge, exchanging stars and gases, eventually merging to form more massive composite galaxies. This concept became known as the hierarchical picture of cosmic history, illustrating the universe's evolution from the bottom up, with structures growing progressively larger over time. A team working at the Subaru Observatory atop Hawaii's Mauna Kea volcano scrutinized one of the oldest galaxies known, whose light has traveled nearly 13 billion years to reach us. It serves as a messenger from a time shortly after the universe's birth. This entity is more than just an object. It represents an entire universe. Termed a quasar, an abbreviation for quasi-stellar radio source, this entity features a small region in its core that shines intensely. Astronomers theorize that its brilliance emanates not from a cluster of stars, but from a single entity at least 1 billion times the mass of our Sun. This luminosity results from gas falling onto the object and heating to extreme temperatures. Such immense power generation is typically associated with a swirling vortex, where space itself is warped by the tremendous gravitational forces at play. Abruptly, the scene plunges into darkness as it merges into a colossal black hole. For astronomers, the pressing question was, how did this black hole attain such colossal size so early in the universe's timeline? It likely originated from an early breed of stars, often referred to as population 3 stars. Composed primarily of hydrogen, they are believed to have been hundreds of times the mass of our Sun. These colossal stars burned fiercely and rapidly, meeting their demise prematurely. A star functions akin to a cosmic crucible. Within its core, the relentless pull of gravity generates such immense heat that atoms are stripped down and rearranged. Lighter elements, such as hydrogen and helium, undergo fusion to form heavier elements like those found in the Sun. Over time, the star synthesizes elements, including oxygen, silicon, and ultimately iron. When the core accumulates sufficient iron, it undergoes collapse under its own weight. This can trigger an outward shock wave that essentially detonates the star in a cataclysmic explosion known as a supernova. If enough material falls into the star's core at the moment of its demise, it can collapse into a singularity, giving rise to a black hole. The emergence of the first generation of stars and black holes unfolded during a period of extraordinary cosmic upheaval. Amidst primordial gas clouds, stars were born within dense clusters, giving rise to black holes that commenced devouring more and more matter. A computer simulation of the early universe vividly illustrates the rapid growth of these insatiable behemoths. Conducted by scientists at Carnegie Mellon University, the simulation aimed to recreate a vast region in the nascent universe spanning over 100 million light-years on each side. It unveils the events of the initial billion years of cosmic history. This virtual cosmos is set into motion by equations delineating the properties of gas, the energy liberated during star formation, and the expansion of time and space. The outcome? A complex cosmic lattice, with gravitational forces attracting matter into intricate filaments and clusters akin to a vast network of interconnected spider webs. Within the densest enclaves lie the birthplaces of the largest galaxies and black holes. Here, annotated circles denote the emergence of black holes within the dataset. As they accumulate mass through their voracious consumption of their surroundings, these circles expand progressively larger. The resultant data is stored in a repository, shrouded in darkness. A select few black holes within the largest galaxies attain staggering proportions, scaling billions of times the mass of our Sun. However, these black holes aren't merely siphoning gas. In a quest to observe black holes experiencing growth spurts, the orbiting Chandra X-ray Observatory was dispatched to peer into distant galaxies. Scientists search for regions of gas and stars emitting intense X-ray radiation. What Chandra discovered was that the cores of certain remote galaxies harbored scorching duos, twin supermassive black holes drawn together by the relentless pull of gravity. Black holes, inherently solitary entities, resist this clandestine union. As the two draw nearer, they enter an orbital dance that could persist for millennia. However, to comprehend what facilitates their eventual merger, we must return to the principles laid out by Albert Einstein. Einstein proposed that when massive entities accelerate or revolve around each other, they distort the very fabric of space, generating ripples akin to disturbances on a tranquil pond. As these ripples propagate outward, they carry with them the energy of the pair's orbital motion, causing the black holes to draw closer. As the dance of death unfolds, the spiral tightens until the pair finally coalesces, birthing a singular, larger black hole. The moment of reckoning may be nearing for a quasar known as OJ-287, situated a staggering 3.5 billion light-years away. Recent surges in activity within its vicinity have led astrophysicists to deduce the presence of another black hole orbiting in close proximity. This secondary black hole, acting as a gravitational anchor, exerts a colossal pull on its companion. Astronomers have estimated its mass to be a staggering 18 billion times that of our Sun. While OJ-287 once held the title of the largest black hole ever observed, it has since been eclipsed. Deep within the heart of the Coma Galaxy Cluster, a mere 321 million light-years distant, lies an immense elliptical galaxy known as NBG 4889. Utilizing several expansive telescopes, astronomers meticulously measured the velocities at which stars orbit the galactic center. This data enabled them to calculate the mass of the central object, revealing a staggering 21 billion solar masses, give or take a few billion. In theory, there are no constraints on the potential mass accumulation of a black hole. Yet, even the most colossal black holes remain giants, and their respective host galaxies appear to adhere to certain constraints. The limiting factors are intricately linked to the evolutionary patterns of galaxy clusters, a phenomenon long observed and studied by scientists. This computer simulation illustrates the developmental journey of a galaxy cluster during the universe's infancy. The gravitational pull exerted by the entire expanse attracts myriad small galaxies, along with vast streams of gas, towards its center. But why doesn't the central galaxy, and the black hole nestled within it, engulf all this material? Why doesn't it swallow the entire cluster? The answer lies within a region known as MS0735, located approximately 2.5 billion light-years away. At first glance, MS0735 appears to be a typical galaxy cluster when observed in visible light. However, X-ray imaging reveals that it is cloaked in a shroud of scorching hot gas, reaching temperatures nearly 50 million degrees Celsius. Within this gas cloud are two colossal cavities, each spanning up to 600,000 light-years in diameter. These cavities could accommodate 600 galaxies the size of our Milky Way. Further examination using radio imaging unveils two immense streams of matter emanating from the cluster's center. This observation provides a crucial clue as to what's happening within. Stars are born from a cataclysmic eruption originating in the core of the massive central galaxy. Two jets, propelled by a central black hole, have unleashed shockwaves that traverse the intergalactic gas medium. The sheer energy required to carve out these cavernous X-ray voids is staggering, estimated to be equivalent to several billion supernovae. In fact, MS0735 has earned the moniker of the largest single eruption recorded since the Big Bang. This cataclysmic event was triggered by a black hole boasting a mass of approximately 10 billion times that of our Sun. Black hole jets, such as the ones observed here, are a phenomenon scattered throughout the universe, even within our own cosmic vicinity. Take, for instance, the renowned M87 galaxy, nestled at the heart of the Virgo galaxy cluster, approximately 50 million light-years away. Astronomers have diligently scrutinized the black hole residing in its core, recently estimating its mass at a staggering 6.6 billion times that of our Sun. This mammoth entity propels a pair of potent jets, cleaving through the galaxy. But how does a black hole, notorious for its obscurity, emit such vast amounts of energy? Picture a black hole as the eye of a cosmic storm, perpetually swirling due to the influx of stars, gas, and other celestial bodies that succumb to its gravitational pull. As matter spirals inward, it coalesces into a rotating, torus-shaped structure known as an accretion disk, acting akin to a dynamo. The rotational motion of this disk generates magnetic fields that twist and redirect some of the infalling matter into high-energy beams, or jets, emanating from the black hole. The magnitude of this energy output is contingent upon the black hole's gravitational force and the volume of matter that has traversed the event horizon. But is this spectacle merely a frightening display of nature, or does it signify a deeper cosmic process at play? The most massive black holes in the universe likely formed between 10 and 12 billion years ago, during the era of quasars. By expelling energy in the form of jets, they heated the surrounding regions, preventing gas from collapsing into central galaxies and facilitating the formation and expansion of smaller galaxies on the periphery. Yet, the influence of black holes extends beyond mere galactic boundaries. As evidenced by Chandra's image of the Hydra A galaxy cluster, colossal hot cavities, illuminated in X-ray brilliance, are evident, alongside a jet erupting from the central galaxy. Analysis of gas along the jet's periphery revealed heightened concentrations of iron and other metals, likely forged within the core by supernova explosions. By dispersing these metals into distant reaches, black holes seeded remote galaxies with the necessary elements for star and solar system formation. This symbiotic relationship persists in phenomena like Centaurus A, colloquially known as the Hamburger Galaxy. In X-ray imagery, a jet emerges from its nucleus. Although shrouded by dense dust lanes, astronomers surmise that this spectacle represents the merger of two galaxies. Computer simulations illustrate the transformative effect of such mergers on black holes. As galaxies collide, the gravitational tug disrupts their spiral forms, driving vast quantities of gas into their cores. As the black holes gorge on this influx, they emit shockwaves, expelling loose gas beyond the galaxy's confines. In the culminating stages, the black holes coalesce, releasing a final, cataclysmic burst. It's awe-inspiring to contemplate that our Earth, our solar system, and ourselves are indirect beneficiaries of these distant titans. The largest black holes have played dual roles in an epic cosmic saga. Indeed, black holes are the result of gravity's unyielding pull, the force responsible for gathering matter into galaxies, clusters, and the intricate structures they comprise. However, despite being born from the relentless grip of gravity, these enigmatic entities wield extraordinary power. Through the emission of immense energy, they exert a formidable force that counteracts gravity's influence. In this remarkable interplay between gravity and energy, black holes have emerged as the master architects of space and time. Their gravitational dominance shapes the fabric of the cosmos, sculpting the trajectories of stars, galaxies, and even light itself. Yet, their prodigious energy output serves as a formidable counterbalance, influencing the evolution and dynamics of the universe on a grand scale. In essence, black holes stand as cosmic juggernauts, simultaneously shaped by the laws of physics and shaping the very nature of reality itself. They epitomize the intricate dance between opposing forces that governs the cosmos, embodying the intricate interplay between gravity's pull and the boundless energy they unleash. Subscribe, comment, like. Thanks for watching. Until next time.